So basically, our intuition tells us that we want to talk about differentiable things. We want to be able to take the derivative of things. I mean, we've been doing it physics in our physics classes all along, like whenever we draw this, and we have like a guy here, or sorry, a ball, and you throw it off the cliff and it's got this. And then like if I tell you, like you want to ask questions like what is the speed using like a bunch of data from the displacement. But that implies that the chart I've given you behaves nicely and actually reflects the real world, I guess. Specifically, what we would care about is like three things. So we care about curves, we care about functions, or I guess this is more examples. There's probably more, but these are the big ones: functions and maps. And with all of these, keep in mind, this would be like, okay, a differentiable curve, a differentiable function, a differentiable map. So I guess just to give intuition for what each of these mean, a curve is just like if I was to throw a rock. So
like
space-time, space-time would be 4D, and then I'm going to throw a rock. And so it's like, if I have like the sphere or something, then a curve is just something like this, right? And it's actually represented as a map. I don't know, we'll pick a random letter. It's a map from R to M. So if you think about that intuitively, it's like, okay, maybe R can be considered intuitively as time, and then M can be considered the space, right? So it's like, okay, as time goes on, the particle moves along. Or I like to think of it as a slider, right? This is a slider that you control, and this is the position of the resulting object. So you slide the slider forward in time, backwards in time, and it moves it along. So that's like what a curve is, quite intuitive. Next one is a function, which actually like pops up all the time later. But a function, you can think of it, well, okay, first of all, maybe without intuition, it's thought of as a map M to R. So which is actually the opposite from R to M up here. Okay, maybe that's meaningless on its own, but intuitively, a really good example is a temperature distribution. So for every single point of the manifold, you associate a temperature R. So this function, first of all, we were talking about differentiable. So a differentiable curve would be a curve without any hiccups, right? Okay, clear enough. A differentiable function would be a like heat graph that didn't, go crazy, do any crazy discontinuities.
So like if the temperature here is like, it's like smooth, like if it's like if you can think of like the heat as like, if you thought of like, if you tried to like plot heat with like color, you would see like a smooth gradient. Whereas like non-differential will be like at one point it's like red and the other point it's like blue, like right next to it, like that.
Yeah, that's an issue. So that's a function. And then I guess maybe just to quickly talk about it, a map is just, I don't know what letter to put here. So I'll put maybe not capital M. It just goes from one manifold to another. So intuitively, this does come up later. This is actually the entire idea behind diffeomorphisms, like being able to have a map like this between two manifolds. I guess we'll visit it later, but I don't know. I guess the word map is always relevant. Okay, but what I really want to emphasize is that this idea of differentiability differentiability on manifolds is not like this crazy thing up there in mathematical la la land. This is like, it's very grounded. Like intuitively, if I tell you this is the curve,
you want to be able to like assign, like, hey, this is the velocity like, what am I doing? Yeah, like at this point, this is the velocity. At this point, this is the velocity, like stuff like that.
Then the question is what happens here, right? So
yeah,
it's just intuitively, it's so easy to see. Like if I give you a sphere and then I draw you a curve on the sphere, you can right away tell if it's like differentiable or not. And the point is, it's really grounded. Like all of this stuff feels like, crazy almighty stuff, but
it literally is like, is it smooth or not?
Yes.
And like intuitively, we know what smooth means. Like it's almost like if it was a real.
No. We know what smooth is for any RD, right? Yes, intuitively, because that's what we live in, right? The issue is defining smoothness on M. But it turns out that defining smoothness on M becomes a piece of cake when you realize that the definition of M includes an entire statement about any neighborhoods being mapped to like a subset of RD. So that means that like the manifold locally looks like RD. That makes our life a billion times easier. And to me, that intuitively shows that this entire idea of smooth manifolds or doing like calculus on manifolds should be possible, like algorithmically. I don't know. I like thinking in terms of algorithms. If I was a computer programmer, this would be possible to do algorithmically. Like it'd be complicated, but I don't know, possible. I don't know. I feel like I need to emphasize this because for a long time, I thought that actually taking a derivative on a manifold was like so far out.
Yeah,
But
but it's
it's
like,
like it's easy, right? You just have like a sphere, and then you take like a derivative of this curve. It's just going to be like an arrow, like, and that's like an actual operation you can do. I don't know. Maybe I'm emphasizing this too much, but in any case, I'm still motivating smooth manifolds. Maybe I'm going a bit off topic. I don't know.
no, that's cool. Last time we were kind of stuck on, so let's say we have like a manifold that looks like this, right? And then we were like, is this like differentiable? Well, the thing is, it's not a manifold that is differentiable. It's like curves on the manifold, right? Or wait, no.
Okay.
So like,
interesting.
so a curve on the manifold would be something like this, right? And it's one dimensional, so there's like not much choice I can make here. But it would look something like this. And the thing is, so this is what I was thinking recently, like just before today, like we started. It's like this like blue manifold right here is topologically, wait, what? Hold on. So yeah, this is topologically isomorphic to,
Okay.
like if this had like ends on each side, like this is topologically isomorphic to, and let's say I had like the standard topology on this, right? This is topologically isomorphic to this. So in reality, like this red curve is basically just this. And it's weird to think about, right? Like in one dimension, but I feel like if you do 2 dimensions,
I don't know. I'm not sure. Like what's coming up in my mind right now is imagine a circle and then a circle with the hat. Okay, that's I don't know. Wait.
Yeah, so that's the thing. I'm pretty sure like that circle with a hat is topologically isomorphic to the circle.
Oh, topologically 100%. But there is something different about them on the smooth manifold level. Like they're not diffeomorphic, I think the word would be.
Is there though?
I'm like very confident that those two are not diffeomorphic. I mean, there's a fold, like there's a cross or whatever in one of them.
True. Because like I was thinking like,
topologically 100%, they're homomorphic.
Because if you lived, for example, on this surface, like would you notice this point? Because like this is like part of your world. That's like this is like really hard to explain like how I'm thinking of it, but it's like, for example, like when you're on this circle, if you kept walking on it, you would never notice that it's curved. It would seem straight to you. But no, that's a different thing.
No, that like comes. Yeah, that's later. Yeah.
But
right now, on the topological level, it's like a rubber ball or a rubber band. You can stretch it and squeeze it as much as you want. But on diffeomorphic level, you can still stretch it and squeeze it, but you have to maintain any like creases or anything. But I'm trying to think what's the actual difference between these two. So I'm thinking, oh man, that's weird.
Maybe if we like go through and get to diffeomorphisms, then maybe we'll get it kind of. I don't know, like I feel like we just
maybe. No, I'm just so confused because in my head originally I motivated smooth manifolds because you want to talk about smooth curves and smooth functions. But then what the hell is this? How does that fit in? This is like the smoothness of the space itself. Maybe it is the point, yes.
Like maybe that is the point. Yeah, maybe I'll like not, because like I'm still trying to think of. Actually, wait, I think maybe
I figured it out.
Okay, yeah, go ahead.
Remember at the start how I was talking about continuous curves, functions. The third one,
maps. It's about maps.
This is a map. Yeah.
Okay. So it's not this.
So it actually, it's not actually included. Like that. Okay. Oh no, yeah, it's a So yeah. Oh, okay. This is so interesting. Okay, so in the same way, if I give you a circle and a oval. Ooh, that's a bad oval. Whatever. You can imagine the difference. This over here is an MO1. This is an NO2, right? And if I ask you, are these two topological spaces homeomorphic, what would you do?
I would say yes.
Okay, obviously you'd say yes, but if I was to ask you like rigorously, or like give me like an idea of what you'd do rigorously.
Okay, so I think it was there exists a bijection. Yeah,
Really?
okay.
Yeah.
So there's a map. So if there is a map that takes you from this to this, such that the map and its inverse are continuous.
In addition to the fact that M and N have an isomer or a bijection.
Yeah, and that they're set and that they're a bijection. Yeah. So basically what that means is that basically turns out to the fact that you can sort of continuously deform one into the other. That's
okay, but I want to.
But that's
but
for
also,
manifolds.
Yes. No, for topological spaces. We're not talking
no,
about
like the
yet.
idea of I think deforming them is like a manifold thing.
I think it's topological spaces. Like I can give you a sphere.
Because like topological spaces, you could even have like stuff like, you know.
Yeah.
Yeah, right. So it's like it's hard to think of like deforming them.
Oh, okay. Okay, let me think here. Okay, a manifold is a topological space. Like as a not powder, but as a structure, they're both the exact same. If I give you a circle manifold and a circle topological space, like as an object, they're both the exact
they're
same
structurally thing. Equivalent, but like
yeah,
a manifold has.
I would argue
it's a type.
Idea.
A manifold is a type of topological space that has like certain conditions that satisfy certain properties.
Sure.
Right? So,
but then the idea here is still valid for just normal topological spaces.
Yeah, the idea is similar, but it's like you can't. It's hard to think of like, you know, like mushing something and like deforming it, like just so intuitively.
I see. So I think
it's just that for manifolds, I feel like it results in that visualization where you can deform one into the other.
I see. Basically, if we were talking about our print function here, it's kind of like if you want to print the idea in your head of having a ball smooth into something, then it has to be a manifold, clearly. Yeah. But the idea of like deforming abstractly, I don't know, is still valid for topological spaces.
It's almost like this is like this definition with the bijection. I just erased that's. But yeah, that definition is like the rigorous way of deforming something almost like this, and then bijection. This is so bad, but yeah.
But also, wait. I want to clarify something. Okay, I know I'm like erasing, but it's because I want to like just about to demo something here. Okay, what does it mean for these maps to be continuous? It means that's what the pre-image of open sets are open, right? In both directions, which means that the bijection is a statement about M here and N, whereas the continuity is a statement about the O's and maybe partially the N's as well. But it's useful to think of it as a statement about the O's. Now, what I was going to say is a diffeomorphism is basically the exact same thing, except you have to remember that this is now an atlas. It includes an atlas.
Aha.
And so diffeomorphism is telling you, okay, keep all of these things, the bijection, keep the continuity, but I also want this extra requirement that has specifically to do with the atlases, which I think the requirement is that if you were to merge the atlases, then the new atlas would still be like, okay, you know, it would be like messed up.
Wait, actually, now I'm trying to like think of something. So if this like map, right? Oops. If this map over here, if we're talking about like the M and the N, right? How do we say the pre-image of an open set? Like, because the map does the map act on the, like, how does the map take an open set to an open set, or does it take like like a point to a point, or is that like the same thing?
Interesting.
Because actually, it acts on the topological space. So what does that mean?
So wait, no. First, the question is, are these two circles homeomorphic? Answer being, they are homeomorphic if that map exists.
But the question is like, what kind
of
what
would that map be?
Like, is it a map from like is
I
it
think
a
it's
map
just a
like
map from the points. Yeah,
is
from
it a
the
map
points,
from
yeah.
M to N
Yeah, yeah, yeah.
or O to
Well, it's
O?
a bijection that preserves continuity.
Because if it's a map from M to N, then how do we say the pre-image of open
Yeah,
sets?
yeah, yeah. So you'd say the pre-image of a point in N. No. Oh, interesting. Okay, one sec.
Yeah, because I was like thinking about this recently. Like, wait, I don't know if I understand continuity well enough.
No, because I think it's a statement about, because remember, open sets are just, or sorry, yeah. The topology is just a subset of the power set of M, which means that it's kind of like neighborhoods. Like every single one of these open sets is like neighborhoods, which means that you can take the pre-image of just a point.
Or you can take the pre-image of like a neighborhood containing the point.
Wait. The pre-image of open sets are open. Okay, sure. So basically, let's say I take the pre-image of this point, and this point is not a part of the topology.
No, the point would be a part of it.
No, just pretend. In this case, let's say I have the discrete topology, okay? So pretend that the point here is not, oh, Jacob's entering. Pretend the point is not a part of the topology, then I would argue that for this specific instance, it satisfied the rule that the pre-image of open sets are open. Because this isn't even an open set. P isn't even an open set. So of course the pre-image of P, like, you know what I mean? The statement, the pre-image of open sets is open.
No, wait. The pre-image of, wouldn't the pre-image of P be the empty set? Or is that not?
Oh yes, it would be. But the point is that
means P, it is open.
But the point is P isn't even open in the first place. Like the statement,
the pre-image of open. So we're not even considering, right?
Yeah, we don't even care about it. So I think what would happen is you would just test the pre-image for every single point in M, or every single combination of the point in N, you know, like power set or something, which would happen to match up with the topology. And whatever they are open sets, then you check the condition pre-image of open sets are open. Okay, very cool. I guess back to the topic. That was like a great tangent. The big point that I missed last time is that, first of all, let me start with like a quick high level. The high level is that, okay, we have the structure MO, and the question is this enough structure to define differentiability? It would be really nice if it was, like extremely nice, because then we wouldn't have to do it, but it's not. And so it turns out we're going to have to make choices. Specifically, the amount of choice we make depends on the dimension, which we'll see in more detail later on, specifically what we saw at the 1 question mark. Okay, so it depends on that. The point is we're going to have to make a choice later on to have the niceness of differentiability. But basically, okay, everything relates back to the fact that the way we define differentiability at first seems super, super, super ill-defined. Basically, what we say is we say a curve. I'll use a curve as an example, but this could be for anything. A curve is diff on M. So a curve is differentiable on a manifold if it is, maybe this should be an if with two Fs, because I think that's the double implication arrow. If it is diff on a chart. Okay, I want to be very clear. What I've written down is ill-defined. Like,
it's not the correct answer.
Yes, but it is a great motivating example. So it would be very, very nice if, like, let's say I threw this pencil and then we saw on a chart that it was differentiable. If instantly I could tell, okay, it's differentiable in real life. The issue is that some charts refuse to behave nicely, right? Like, charts don't have a limitation in how messed up their map can be, right? Like, let's say I'm charting the city of Toronto.
That's true.
Yes, this is where everything comes back to this point, right? In theory, charts can behave nicely, right? like where whatever the continuity or sorry differentiability of Toronto gets preserved. But some charts are going to just compress the hell out of different things, or add some folds and just refuse to behave nicely. And we don't like those. If we could come up with an atlas without those charts, then this definition would be valid.
But choosing that atlas is a choice that you make.
Well, in some dimensions, it's not a choice, right? Because you've only got one option.
This is actually something that I wasn't too sure about. Like if I have a manifold and then a curve on that manifold, when we say that it's not differentiable under certain charts, do we mean like, okay, actually, let's say I had a curve like this. Like if I took a chart that takes this part and then maps it onto RD, like are we saying like this is a problem because the curve is differentiable here, but it's not differentiable on this chart? But it's actually a little more than that.
Oh yeah.
Because it's not, because the thing is, even, and that's what I think, like even just this, like even if I just took like this part of the curve, even on a certain type of chart, this part could turn out to be like
messed
having
up.
a spike.
Exactly.
Yeah. And it's because the charts can it's just a map, right? Like your map can be defined in a weird way.
Exactly.
Like you might say, okay, this point, we're just going to put it like everything over here, we're suddenly just going to stretch it downward for some reason.
Yeah. And then boom, now you have a fold or whatever it's called, a crease. So all of this weird thing that we're about to do with atlases and making sure that atlases are flower compatible, it's all about getting rid of the atlas or the charts that don't cooperate. Mm-hmm. That's it,
So we're just defining it based on our definition. It's not actually it's almost like it's not like a holy definition that's always differentiable all the time. It's like it depends on what charts you choose to put in your atlas.
Exactly.
As long as the charts cover the whole space.
Like this over here is so simple, like if I showed you the chart of my pencil flying through the air and it looked differentiable on the chart, and you could immediately say, oh, hey, it's differentiable in real life, that would be great. Unfortunately, it's not the case. Unless I tell you, like, let's say I guarantee you, I'm like, okay, all the charts I have in my bucket here or in my book behave nicely. Like I give you that guarantee. Later on, we'll see like what exactly this behave nicely means mathematically. The short definition is that any intersection between U and V will end up doing something special. Well, what is it again?
So either I can actually explain this a little bit, but I don't know if we should do that right now. Okay,
do it.
So what we're looking at is, so U and V are charts, right? It's actually U, X, right? Because charts come with a chart map. So we've got U, X, and V, Y. So.
Oh, wait, I think I got it intuitively.
Wait, so U is actually is U like a set or something? Like I'm like blank here for a second.
Oh yeah, U is just a part of the topology, like it's a neighborhood.
So basically it's either, so the intersection is either empty. This is one possibility.
Oh yeah, but that's clearly because they're compatible. Yeah.
So that's because like if I have a manifold like this, I just want to draw a picture. If I have a chart that takes a look at this part and a chart that takes a look at this part, because they don't overlap, there's no way for there to be any conflict. Like for all you know, everything's fine. Not even for all you know, like when we're talking about compatibility, we mean like, are they giving us conflicting information? And in this case, they can't be because they're talking about two completely different things. So that's one case, and that's the easy one, of course. The other case, I'm just going to erase off this actually, is, so if the intersection is non-empty, then chart transition maps have to have this flower property. So let's see, we've got a chart. So we've got U intersect V, right? So it's like we've got this manifold, and then let's say we have some kind of curve, and we've got a chart U that takes a look at this part, and a chart V that takes a look at this part of the curve. Okay, so I'll actually say that V is yellow, U is green. So what we're trying to do is say, so we can map this. What we want to do is understand this overlapping region. And the way we do that is by mapping it. So we use this chart map X to take it to, I believe it's just, yeah, it's just X of that. So like it could be like whatever the map is of that intersection, right? Or we can use the map Y to take it to, so we're using the map X to basically understand it in the U chart, or we're using the map Y to understand it in the V chart. And that's basically what the maps do. Like they take this part onto U, which is like a Cartesian axis usually, or V, which is another Cartesian axis. That's what the X and Y do. And what we want to do is check if hold on, let me see. Chart transition map. So chart transition map, there are two of them. So one is this way and the other is this way. Yeah.
Our flower.
Yeah, so this one here would be, so this one is, yeah, this one is actually, yeah. So Y after X inverse would be this one over here. And X after Y inverse would be this one. Because it's like Y after X inverse is like going from here to here. And then X after Y inverse would be going this way. And we want to check if they have this flower compatibility property.
Yeah.
And this flower compatibility property is how we define differentiability. And this is interesting because both of these charts lead to, so these chart transition maps basically take us from a part of the thing to a subset of RD.
Which is amazing.
Which is amazing because we know because we know what RD looks like.
Yeah.
And because it's a manifold, yeah.
Well, it's not that we know that what it looks like, but it's like we know how to take
yeah, we know how to differentiate.
Well, yeah. Things. I mean, right now we're talking about flower though, but I guess this is like, okay, later on we know we're gonna want flower to be whatever differentiability. So
yeah. So this is actually pretty intuitive. You take like an intersection of two, so either two charts don't overlap, in which case there's no conflict, or if they do, you want to check if their intersection. Basically, if you go from for their intersection, if it looks the same in both charts, if they're differentiable in both charts, kind of. Mm-hmm. Is that how it is? Is that what this means?
That was exact. No, okay. How about this? I was just thinking of an intuitive way to state like this, and I came up with this. So if this is our original statement, which is that, you know, like if it's differentiable in the charts, then it's differentiable in manifold land, which at first wasn't true. Basically, the guarantee that this upholds over here with flower compatibility is saying if one chart shows that the curve is differentiable, then the other chart better also show that it's differentiable, you know?
Yeah, that's basically what it's saying. So you're basically, we're trying to choose charts such that it looks differentiable on all of them.
No, well, more than that, we want it to be the case. Like, we want it where, like, it must be that way. Like, one chart must imply that every single other chart in the atlas.
Yeah, the charts must agree with each other, basically.
Yes, exactly. Like, yeah, if one chart says that it's differentiable on the manifold land and the other one says it's not differentiable on the manifold land, what?
Yeah, exactly. We don't want that.
Yes. So what we do is like we get them to agree beforehand. It's like if I give you my big bucket of charts and I tell you, this is the guarantee I tell you, all of these charts agree on the differentiability of curves. Okay, in this case, if the flower property we care about.
And it's also like the differentiability of certain curves. Like certain curves will look differentiable in this atlas, but not in another atlas, and vice versa. So it's almost like yeah. So basically what this whole thing is doing is like we're creating an atlas out of charts that agree with each other on the differentiability of curves.
Yes, so that this becomes true.
Yeah.
Or like is true.
But again, like the choice we make influences which curves we consider to be differentiable.
Maybe I disagree with that.
Okay.
Um,
Okay. Here's
why?
what I'm. So like, let's say, like if I throw an object, right, and it makes. Actually, can I clear this?
Go ahead, yeah, clear the thing.
So
Or
let's say
clear
I.
everything. I'll clear this. Sorry.
So let's say I have an object that makes a trajectory. You would agree that there are some charts in the maximal atlas for which this trajectory is not differentiable, right?
Yeah, messed up charts. Yeah, the ones that refuse to
There are
cooperate.
messed up charts. Wait, what do you mean? Like they refuse to cooperate according to the way we want them to cooperate. There are many charts. There are many charts that are like this. There are many charts for which this curve is not differentiable.
Okay.
So theoretically, you could take a bunch of those charts and put them together into an atlas, because there's probably enough of those non-agreement charts that could span the space. And if you do,
Wait, you want the ones that agree?
So you want charts that are compatible with each other.
Oh,
But
okay,
there are
sure.
charts that are compatible with each other that don't call this curve differentiable. In other words,
But no, this is the point is this curve exists in manifold land. And in manifold land, it either is differentiable or isn't. So like, yes, I see what you mean by chart land. It'd be nice if chart land can like agree with themselves, but at the same time, you might have a chart land that is just wrong, you know?
yeah. So you would have a chart line for which, but you might have a chart line. You can have chart lines for which curves that should be differentiable in the real world are not differentiable in your atlas. So
Wait, repeat that?
you can have an atlas that doesn't reflect the real world well.
Okay, but
But you don't want to use that. Like theoretically you can.
not only would I not want to use it, but if I did equip a manifold with that messed up atlas, would this be a smooth manifold? Intuitively I say no. Practically I'm not sure. Maybe it is. That's so interesting, because you're right. What if you just make an atlas of
so that's what I'm saying. Like this is what I think the idea of like choosing the wrong atlas is, or like choosing because like that's where our choice really is. Like we want to choose the correct one for which curves that are differentiable in the real world are differentiable in our atlas.
But we haven't actually tested for that. All we've tested is that charts are compatible with themselves. But what if all the charts are compatible with themselves because they're all wrong? You know?
Yeah, exactly. That's what I'm saying. Like for all we know, we might choose charts that are compatible with each other, but all together collectively wrong.
Exactly.
So that's what the experiments are for. Like that's what the choice.
Oh.
Yeah, like when they say like there's a finite number of choices you can make. And this is for, certain dimensions where there is a choice, right? Like for 1, 2, and 3, there's only one choice. Like there's a choice, but only one correct choice.
Do you think that's...
I think that's how it is. Like that's what I understood from it. Like, because that's what you're saying. Like you want to like we can do experiments and figure out which one is wrong. So I'm assuming like that's what the experiments are checking for, to check if the atlas you have chosen is correct.
Okay, well, okay, how about this? Okay, I'm not sure that total statement is true yet. It might be, but there are a couple of concerns I want to address. Number one, as a very simple example, if we have a chart map, like whatever, it takes A to A, and then takes A to A cubed. Like, okay, just imagine that, like right now I'm speaking in intuitive land over here, okay? Imagine charts that just look normal, and then charts that do this A to the 3 thing, that somehow like zoom in as you get farther away. Or I don't know. Like, charts that would be...
Yeah. It would do something.
Yeah. The point is the chart would be like weird, okay? I would say that this, whatever, the total atlas of charts that like conform to this and the total charts that conform to this by themselves are strong enough to say like the pencil I throw, its thing is continued. Like, what am I trying to say? This atlas over here is strong enough to predict if something is differentiable or not, if a curve is differentiable or not. And this one is as well. But as soon as you put the atlases together, they're like incompatible. But they're still both accurate by themselves. So it's like if these, I think the proper thing to say is that these are the same up to diffeomorphism. But then what you're talking about, like about choice, because I don't know, this doesn't feel like a choice because they're like kind of the same. They're both check marks here.
You're choosing, so you need to take charts that are compatible with each other, right? Like that's, like we're deciding like,
Yes.
okay, we want charts that are like, we're creating an atlas of, we can create an atlas of charts that are not compatible with each other. Like that's a thing you can do. It's just that we don't want to do that. So number one, when we do physics, we take charts that are compatible with each other so that the world makes sense.
Can I go through, let me go through the definition and see if that's actually a requirement for, like, okay, you know, like a smooth manifold is M, O, and A, right?
Mm-hmm.
I'm very curious, is there a requirement for the A to behave nicely as we're talking about? Or can it be like extremely messed up?
Because a smooth manifold, so a smooth manifold is a topological manifold with a C infinity atlas. Isn't that what it is?
Oh, which means the atlas has to be C infinity. It's not any random atlas.
Yeah.
Aha, okay, that's where I was confused.
Okay, actually, should we just like talk about flower compatibility real quick?
I don't know. I don't like the approach of flower compatibility to me. Like, no, like it's good for intuition. I don't know. Here, how about this? You explain to me.
Okay. Wait, clear.
I'll clear the board. Yeah. Okay.
Okay, so an atlas A flower is a flower compatible atlas if, so you've got this atlas A flower, right? That's a flower.
Like, wait a sec. How about this? Maybe just for intuitive reasons. Imagine I have a bucket of charts in front of me, and I tell you like,
yeah, okay, boom. I've got like a notebook of charts. I pull out two charts. So let's say what flower compatibility is, like a flower chart, like an atlas A flower is flower compatible if I can take any two charts.
So you pull them out, yeah, from the bucket.
Any two of them, right?
Well, no, first you actually need to insist. You need to be like, hey, I guarantee you this bucket has flower compatible charts. And then you start doing the proof.
Yeah, and the proof is that I can take any two of them and those two. So like, let's say the flower is C0,
okay, if they
right?
don't, wait, pause. If they don't intersect, it doesn't matter, right? If the two charts you pull out don't intersect, irrelevant.
Yeah, okay, because like we know that, okay, if we take out two charts that don't intersect, they're always going to be compatible. So let's say that I'm always going to tell you to pull out two charts that intersect, that have an overlapping region, right? So whatever charts you pull out, you're going to get something like this, and they're going to have an overlap. Okay, so let's say my atlas is C0 compatible. Okay, this is like, which it is, but they all are. But so what that means.
What guarantee are you basically telling me about those two charts?
I'm guaranteeing that. Actually, the maps from one chart to the other are continuous.
What does that mean, though? Oh, I have an intuitive way to explain this, I think. Wait, Avnish, I think I have an intuitive way to explain this.
Okay.
The intuitive way to explain this is that pretend that this has a curve going through it, through the intersection. What it means for those two charts to be flower compatible, let's say C0 compatible, is that the charts have to agree on the status of that curve.
They agree that the curve is continuous.
Yes. Like they have to be capable of agreeing, you know? Like, you know, I could draw a curve that is not continuous, and they both have to agree, hey, this curve is not continuous.
Yes. And for
but
them to,
not for a specific curve, for any possible curve.
yes. And what that means is really that on U, if I plot this curve on some chart, and then on V I plot this or on another Cartesian axis, that they're both continuous basically in each of those respective axes. And that I can go, which means I can go from this curve to this curve. And it's in a continuous way.
Mm-hmm. Okay, sure. So that's what it means if I tell you I have a C infinity atlas with me. It means whenever you
No, it means it's a C0. Well, this is C0.
No, this is C0, but I'm talking later on, right? If I bring to you a C infinity atlas, it means that you can pick two random atlases and they're either going to not intersect, which, okay, whatever, they're compatible. And if they do intersect, then it's a guarantee that those two charts will both cooperate on their decision.
Yeah.
Whenever you have a curve passing through them.
So then C1 would be those like that if a curve is differentiable on one chart, it's differentiable on another chart. Like differentiable once on one chart, it's differentiable once on the other chart. So both charts
I think that's more of an implication. It's more like the both charts agree, which means that if it's differentiable
so that
on
like
ends.
yeah, so that would be C1 means that both charts would always agree that
that
like
any
if you
curve
give if you
or
give
any
both
function,
yeah, like if you give both charts a curve, they will both agree on its differentiability. Like they will both
status,
agree
yeah.
either this is like if I give them any random curve, they will agree that this is not differentiable.
Yeah.
Or they might agree that this is differentiable. They might,
I don't like that though.
but that's a bad chart. Like that's a bad chart, but if they're compatible, then they would agree. Like as long as there's an agreement.
I don't know. Let's entertain this. I want to believe that that's somehow not true.
No, because compatible does not, just because two charts are compatible doesn't mean that they are good.
Yes.
What I would say. Like I could have,
oh yeah.
like I could have an atlas of Toronto, right? That looks like, so each map in that atlas looks nothing right like Toronto.
Yeah.
Like I could have that.
When you compose
but as long as you overlap, like as long as like let's say like it says like okay the CN tower is over here, and then the other chart and there's like a tree over here and a tree over here. That looks weird. Let's say like the CN tower is over here and there's like a tree over here and a tree over here. Like let's say one chart says that, and then the other chart also says that, but it's like in a different place. Like maybe the tree is like over here at the bottom, and then the CN tower is over here, and the tree is over there. Like maybe this is one chart, like the CN tower is on the left, and then this is another chart, the CN tower is on the right. They still agree.
What does this have to do with flower though?
The idea is that sure they might agree, but for all we know, like maybe the tree is not to the right of the CN tower, maybe it's somewhere else. Like in the real world, it's like, wait, this isn't a tree. This is supposed to be the Rogers Center.
I see.
So that's what I mean. Like compatibility does not imply correctness.
Yeah. So, but wait, that's compatibility between two charts. But if I give you a C infinity, what's it called? A C infinity. I can't draw infinity. If I give you a C infinity atlas, I hope to believe that all the charts in that atlas, like if I give you a C infinity atlas, and then I show you on this chart that's a part of the C infinity atlas, and I show you a curve on here that is differentiable.
You want to believe that it's differentiable in the real world.
Yes, exactly that.
Right. So what I'm saying is that is something that you have to confirm by doing experiments.
No, I see. What you were talking about is between two charts, right?
Yeah. So you're saying like there's no way all charts can be compatible?
I hope. Okay, I don't have any proofs here.
Because
like that would suck.
Like because I'm like I could totally draw an elaborate it's almost like you're creating like this perfect lie. Like I could I could totally write like
maybe
book.
The lie is so perfect that it becomes a truth.
Yeah.
I don't know.
Like maybe I'm just like
Wait,
this
no,
atlas.
legit. What if the lie is so good that it becomes a truth? Because it's like everything would be wrong, all the charts would be wrong, but in total, because everything is so wrong, it's still able to tell you whether a curve is differentiable or not at the global level.
Maybe, but like, what if? Because I'm thinking, like, what if I drew the chart of the Earth in a weird way, such that like I threw a ball and it doesn't look differentiable, but I could.
In the real world?
No,
Or
hold
where?
on. No, never mind. So like, let's say I threw a ball in the real world, and then I looked up its trajectory in my atlas, and maybe that trajectory is not differentiable. And then I'm like, I know I can perform an experiment and calculate its velocity at this particular moment, so I know that it must be differentiable. That's what
Can you
I like.
explain?
Actually, I don't think this is making sense, but like what I'm saying is like when he says, like just because something is C infinity compatible, like that's what I'm saying. Like maybe it's just like a perfect, like a really good lie.
I know.
Like I don't think that it necessarily implies like, hey, because especially because like to be C0 compatible, like remember like the whole Whitney theorem, right? Like if I have an atlas that is at least C1, I can refine it into becoming C infinity.
Yes.
Yo,
But that's unrelated though.
that is unrelated. But because like oh wait, because the thing's like this is also a thing that we do, right? So like let's say
No,
yeah, I don't
Whitney's
know.
theorem to me, Whitney's theorem is just a
Yeah,
thing
Whitney's
that
theorem is like not really accurate.
happens. No, like to me, what it feels is something that happens to be true and that's really convenient.
Yeah.
But I don't know. Like, okay, remember the first phrase at the start, which is that if something is differentiable on chart land, then it's differentiable on manifold land. So clearly that statement's not true, but if I give you the right bucket of charts to play around with, then that statement can be true for C1. But then it's like when you keep on removing charts, because some charts might behave correctly for C1, but not behave correctly for C2. If you can imagine that, I don't know.
I think maybe because it's like we're defining differentiability on manifolds based on differentiability in the atlas we chose.
On the
Like a differentiable manifold requires having M, O, and the atlas.
okay.
So under a choice of a different atlas, the way differentiability looks might be different.
Like, what do you mean? Like, literally? Oh my.
Because
In the real,
differentiability depends on the atlas. Like just like how
yes. I see what you
just
mean.
like how continuity depends on the topology, right? Like if you choose a weird topology,
yeah,
something that looks continuous might actually not be continuous.
crap. Yeah, because we always use like the real world. We're like, oh, in the real world, if the pencil goes.
I think it's the same thing
to
for atlases.
describe
Like
that
something
real
that
world,
looks,
you need atlases.
yeah. So that's what I'm saying. Like just like how something that's continuous under a certain topology might not be continuous on another topology. Similarly, something that's differentiable with one atlas might not be differentiable with the other atlas.
I really don't want to believe that, but I think it's true.
No, but I think like that's the point, right? Like that's the thing. Like that's why we have to choose our atlas carefully, because it's not like because the things like the mathematics is not going to give us physics. Like you can't just figure out how space-time works using mathematics.
Math, yeah.
You need to use like the real world, right? Yeah. Like, that's what I think. Like you can't just be like you can't just start from basic logic of manifolds and be okay, no, therefore like the nature of reality is like this. Like you don't know that.
Okay, so wait, so you're making a choice of charts, but those charts have to be compatible. So the choice you're making is rather.
It's almost like that's not really much of a choice. It's like, yeah, because.
Do you think this is related to the choice 1, 2, whatever, 1, 1, 1, infinity, 1?
I don't know, like because what was the chart? The number of C. Oh. So what that was saying is that was about like the number of C infinity manifolds you can make out of given C0 manifolds. So if you're given a
What?
C0 manifold,
Are you sure?
yeah, I mean
No,
that's what it says.
this is the number of whatever up to diffeomorphisms. Unique
Yeah, up to diffeomorphisms. Yeah.
atlases.
Hold on, wait, what does it say? It says, so the thing you said is the number of C infinity manifolds you can make out of a given C0 manifold up to diffeomorphisms.
Whoa. What line is this?
Like the last line of the notes for gravity.
Oh, gravity and light. Okay. I was on the wrong lectures. Okay, yeah. Your number of C. Bruh. Okay, clearly I don't understand that.
So that basic, so because I don't think I fully understood that either, but like to me that means, well, if you have a given C0 manifold, that means you have a manifold with an atlas that is C0.
Yeah.
The air atlas is C0. And how do you make it C infinity? You take out all the charts that are not C infinity, basically. Like you say, I want this to be.
Oh crap! And that's where the number there comes up.
Yeah. So wait. So actually, let me just like mention Whitney's
Oh
theorem.
my god, that's so cool. Because that's C0 manifolds. So of course that's nothing.
Oh wait, that's C0. Right,
Yes.
right. So if it's C1, like you can make, you can make it C infinity. So an atlas, right? It's just a book of charts.
Yeah.
Right. And if the more charts you have that are compatible with each other, it's almost like the more restricted your rules are. It's almost like,
wait, so number of C infinity manifolds one can make out of given C0 manifolds up to diffeomorphism. So wait, you start with C0, which is just literally a maximal atlas.
yes.
And then that's where the tree pops up, where you can start making.
When you pull out charts, you get more C. Like you get a higher degree of C. Sometimes, not always.
Yeah, sometimes you can't go from 0 to 1.
And Whitney's theorem basically says that if you have an atlas that is C1, which means at least C1, which means every pair of charts, their intersection is once differentiable. So you can take the first derivative of any curve on any pair of charts. Then,
then you can go all the way up.
So then there are some pairs of charts where you cannot take the second derivative of a curve. So you just remove those, and boom, now you have an atlas that can take the second.
Yes,
so
it's like with the charts we were talking about, the charts that don't cooperate. So you can have a chart that cooperates for C1, but that doesn't cooperate for C2, essentially.
Yeah. So you can and then you can just like remove it and say, bam, now it's C2. But when you remove it, you're now you kind of have like a new atlas. You have a sub-atlas, right?
Sure. But I would say at that point, you've passed the point of this crazy one.
But it's like it's not a loss of generality. So like
yes.
Removing those things, it's like it's okay.
Yeah. So the real thing here with 1, uncountably infinite, finite,
it's like finite. You have it's like
that's
if you
going
have
from
C0,
0 to 1.
Yeah, because if you have like a C0, like if you just have a manifold that tells you, okay, this curve is continuous, and you want to find out how differentiable is it, then
so wait a sec. So do you remember the example I gave with a and then a to the power of 3 as your rough intuition here? So those two atlases are not compatible with each other, but for some reason they are unique up to diffeomorphisms. Whereas apparently some whole other class is completely separate, and maybe that's what you were talking about, the big lies. Like maybe the big lies is like that actual difference.
Maybe. Wait, hold on, because like I remember this was on the problem sheet. What was the thing again? Like, are they like up to defeat? Like, wait, how do those things work? Like, what do they come into play? It
was on the problem sheet, really?
Yeah. Well, actually, I don't know if it was the same thing. It was like something about, there was an example about a and a cubed.
Yes, that's where I got my intuition from. Yeah. But those two are definitely the same up to diffeomorphisms. I guarantee it.
Hold on, let me just like try to find that real quick.
It was exercise 2.
Okay, so let's see. Aha.
Oh my God, yes. You know why? You know why they're the same up to diffeomorphisms? Because they agree on their verdict. Their verdict on whether any arbitrary curve is differentiable or not. They agree on their verdict. So of course it's diffeomorphism. But as you mentioned, that's where the great lie comes in, right? You can still have a consistent definition where it just literally disagrees on which curve is differentiable or not. And that's where you get the 1, 1, 1 uncountably infinite. Perhaps.
No, like if it disagrees, then it's not compatible, right? Like if they disagree.
No. All of the charts internally agree with each other. And I'm talking this atlas and this atlas disagree on a curve.
Yeah, so that's the choice. I guess
that's where it goes 1, 1, 1, 1. But if I had an atlas here and an atlas here that agreed on everything, every type of curve, but that were like they're not compatible with each other. That's the a and a to the power of 3 example. Like those two are not compatible with each other, but their verdict is the same. Then they're diffeomorphic.
Yeah. Wait, now I'm starting to doubt myself.
Okay.
So the number of C infinity manifolds you can make out of. Okay, so we're given a C0 manifold with an atlas. And by removing charts, we can potentially get more than one C infinity manifold. Like we can get two different atlases
that is not diffeomorphic.
Yeah, that results in C infinity.
Yeah,
so that's where the choice comes in.
Which so it's like they agree on. I see. So it's literally like they disagree on the verdict.
Yeah, so it's like internally they agree. Like every chart in this atlas agrees that, like I might draw a curve and say every chart in my atlas agrees that this is differentiable. But then I might have another atlas for which every chart agrees that it's not differentiable.
Yeah.
And although, like, wait,
in this case, it's impossible. Right? In this case, because you drew a curve in 2D, there's only one choice.
Yeah. If it was in 4D, then it's
I don't like that. Man, why 4D gotta be so weird?
Yeah. Okay. Wait, hold on. I think, was there something else I wanted to say? I don't think so. Yeah. Actually, hold on.
I'm still gonna have to actually understand diffeomorphisms. Like, are said to be diffeomorphic if. Oh. Yes. So you know what we said about the two guys having the same verdict, then they're diffeomorphic? That's exactly the definition.
Yo,
that's beautiful.
Oh, that's okay. Like, or it's like getting validated.
Yes.
So if there exists a bijection,
blah 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 blah, that are C infinity maps.
Wait.
Basically, when it says that there's a bijection going both ways that are C infinity maps, it's saying like they agree on the verdict, pretty much.
But these are two different manifolds. Oh, yeah, these are two different manifolds. Like two different. Hold on. So we've got M, O on M, and A on M. So that's one manifold. And then we have like a totally different N, O on N, A on N. They're diffeomorphic if there's a bijection. Well, if you can.
No, the bijection is clear. That's just like set theory
level. Like you can, yeah. I think this is like.
No, not even more. That's still like set theory level. But the next point is important. It's where it says that both M to N and N to M are C infinity maps.
So the transformation from one into the other is like differentiable? What does that mean?
Which I think practically translates to they agree, their atlases agree on their verdict. Because the way that maps...
Because things like the atlas is talking about a different manifold. Like the AM is talking about M, whereas AN is talking about N.
Mm-hmm.
So they're talking about different manifolds.
For N to M. But for N to M to
so like a curve on M, like if you transform that into a curve on N using your map, what was this, phi?
Yeah, phi, yeah.
Yeah, this is not the MP set, this is phi. Yeah. if you have like a manifold like this with a curve on it, and you use phi to turn that into a manifold like this with a curve like this, then the differentiability of this curve is preserved. So this curve is also differentiable under this atlas.
No, because phi isn't a curve on the manifold. Phi is the whole manifold. It's M.
Phi is like phi is like a transformation from M to N.
From the whole manifold. Like every single point of the manifold.
Yeah. So what I'm saying, like if you transform this entire curve, and this curve is just like a ton of points, right? If you transform this entire curve and put it on the other manifold, it's still going to be differentiable on this. So is that not what you're saying?
But for every single possible curve, because it's M.
Yes, for every
curve. I agree with you. Okay.
Right.
Okay.
Yeah. So you take any curve.
So they agree on their verdict. Pretty much.
So I say I'm going to use phi to transform this manifold into a different one.
Yeah.
And I'm going to use a different atlas, the atlas that applies to this one. It's diffeomorphic if the curve is still differentiable.
Exactly. Or if they agree.
On all of the curves, like every curve I do.
And they should also agree on curves that aren't differentiable. Like
so if they're not differentiable, then I can't just turn this into a differentiable. Okay, bro, we're getting this. I feel like we're getting this.
Okay, I'm obviously gonna have to like go over this again now that like do the example sheet again, but like with this new perspective in mind.
And this is good because it's like structure preserving, right? So like for sets, I mean we already talked like sets that are set theoretically isomorphic is like if you can pair them up, so bijections.
Yeah. But then for diffeomorphic level or for
so sets are pretty simple. Topologies, it means you can like the map from one to the other and then back is continuous. So again, it's like continuously deforming one into the other. That's the intuition on a manifold level, but obviously for like abstract topologies, it's just there's a bijective map that is also continuous. A bijective map from one to the other that's also continuous. And then diffeomorphic, that's what we just talked about. Like all curves, like taking any curve, its differentiability remains the same.
Wait.
Status made them the same.
There's an issue though. The issue is that consider a sphere and a sphere with a crease. So wait. There's actually two different oh my god, okay. Because look, I can break. Imagine I have a sphere and a sphere, right? Spheres in 3D, not a good example. Pretend I had an object in 4D and an object in 4D. And then I switch up the atlas, which breaks differentiability. Like then
it's the same atlas. It's the same manifold, but different atlases.
Yes. Whereas in the other case, we talk about a circle and a circle with a crease. In that case, it's actually the manifold that's switching with the same atlas. So it's like there's multiple ways that you can break differentiability, or that you can break the diffeomorphism. You can break it on the atlas level if you happen to be on the fourth dimension or whatever.
All the things like you could argue that like if you're using a different manifold, like the atlas itself is different because like the charts will look different.
Ooh. But the definition of diffeomorphisms acknowledges that atlases can be different.
Yeah, so like the atlases will be different. I'm saying because technically like different things.
Let's say you consider a map that goes on the creased one like this and a map that goes on the circular one. Of course, they're going to disagree. Their verdict is going to be different. Like, bruh, the structure.
Yeah, like it's definitely going to be like.
So intuitively, they disagree. The smooth manifolds disagree on the status of that curve. I don't know. Okay, anyways, but I definitely have to do more thinking about this. But like, I don't know. This was like amazing intuition.